Introduction to optimization. I want to briefly introduce what optimization is, kind of outline the types of algorithms that people employ with their benefits and drawbacks, and then talk about what I think is the most important topic here. That's the merit function. The merit function is this single number that somehow quantifies how good your device is if you're designing a device, or how good whatever it is you're trying to optimize. Introduction. So what is optimization? Optimization is we have some function and we're trying to find minima or maximum. So I plotted a little function here and there's a maximum sitting right at a point, and we're trying to figure out what values of x and y get us to this maximum point. So this function isn't normally something like just a closed form Gaussian, right? Because we know where that maximum is. This function is usually the result of a simulation or some kind of complex calculation. And it's a measure of how good this thing is that you're trying to optimize. And it goes by many names. It's called a merit function. It's called a fitness function. It's called a quality function. It's called a cost function. And it all really means the same thing. It's this single number that quantifies how good the design is. And it is extremely rare that we're optimizing closed form equations simply because we usually know where the peaks and valleys are of a closed form equation. So more often it is the result of a simulation or something complicated like that. Here's an example from electromagnetics, and I apologize if you're not an electromagnetics person, but we won't go too deep into this. So there is what's called a diffraction grating, and it's a periodic array of teeth. We're showing one unit cell. So imagine what is shown in blue here being repeated infinitely. And when a wave comes into a diffraction grating, the diffraction grating will split that wave into discrete directions. In this case, the period, or the spacing from tooth to the next tooth, is 1.75 free space wavelength, or just a little over 1.5 wavelengths. That's what ensures we only diffract into 3 modes. Now there's some design parameters here, and the two that I've chosen are the depth and the width of this tooth relative to the grating period. And what we would like to do is figure out what values of f and d lead to no power going into this is called the 0 order mode. So all the power from the incoming wave actually gets coupled into these what's called the plus and minus 1 order diffraction orders. So we want to somehow design f and d so that no power ends up in that 0 order mode. That's our example. So we come up with what we call the solution space. We have all values of f and all values of d. So if we pick a point on this plot, that corresponds to a particular design. So right here, we have a relatively small value of f and a relatively small value of d. So the small value of d leads to a very shallow tooth. It's not very thick vertically. And the small value of f means it's also very thin. On the other extreme, we could be way out here. That's a high value of f and d. So high value of f means it's very wide relative to the period, and the high value of d means it's also very tall. So all solutions we're interested in somehow fit into this solution space. Now, one thing we could do is called an exhaustive search or a complete search, and I did do that here. So I simulated all possible designs over all values of d and all values of f, and I plotted here the diffraction efficiency, or how much power has gone into that 0 order mode. And so there is no power when we have dark blue, and we see a bunch of regions for that. But anyway, look how complicated and crazy this is. So that's very typical of when it's the result of a simulation, not a closed form answer. And so where is the best place in here? What has the lowest diffraction efficiency? And maybe we'll choose this. Is this the best? Or maybe not. Maybe something like this is actually where the best is. Or maybe somewhere else. And so there's actually some more things we should consider. One of them, for example, is how broad is the solution? Notice, okay, we get a dark blue here, but it's very thin. That means it's going to be very sensitive to the depth. And if our manufacturing tolerances are not that great, well, we might actually end up with a poor design. Whereas here, the blue, maybe it doesn't go as deep as this, but it's nice and broad. And so that would be more easily manufactured. Here's a different way to visualize that shows actually how crazy this solution space is. And this is a great example. This is very representative of what we normally see. And we have to somehow search this to find the absolute best solution and not get trapped into little local minimums. For example, here's a little local minimum, and we could easily get trapped here and miss these others. And well, that's a problem, and getting stuck in local minimum is a huge problem for optimizations. So each of these solutions is what will be called a local minimum or a local best, and the goal of an optimization is to find the overall global best. Problem is, unless we know more about the solution than we're really leading on, there's no way we can be sure that we have a global best. If we're using some kind of stochastic random optimization, it's probably because we know very little about what the global best is. And so, well, fortunately, we're engineers. As long as we get a design that's good enough, we're satisfied with that. But we can never really say that it's the absolute global best. So let's get into some common optimization algorithms. They're divided into two main groups. The first group is the direct methods. These do not involve any kind of randomness at all. And so we've already talked about the first one that we did, the complete search. And this is really the only way that we can be guaranteed to find the global extrema. And we might ask, why don't we always just do a complete search? I mean, I did it on that last example, and that just happened to be an example that was quick to generate. Imagine each simulation would take a week, and that plot probably had, I'll guess, 100,000 points on it. So do the math. You'll never, ever finish that. And so complete searches are possible sometimes, and if they are possible, heck, do them. But very often they're completely impractical, and we only talk about them academically. The next type is a gradient method. And this is not good for finding global best, but if you have sort of a close guess of where that is, the way that works is you pick a point and you look at the gradient. You figure out which way is going to the maximum or minimum, depending which way you want to optimize, and you move in that direction based on the gradients. So this can zoom in on a local best very quickly, but really can't be used to find the global best because it's not really searching globally. And so if you have a crazy solution space like we showed on the last slide, that's definitely not going to work for you. The whole other half of this is the stochastic optimization. Stochastic meaning random. This is where we're employing randomness. And we'll use these and prefer these when we know very little about what the absolute best solution is. And maybe it looks crazy like on the last slide. This is a great place for stochastic optimization. So there are many, many different types of stochastic optimization. I can touch on a few that seem to be more of the popular ones in electromagnetics, which is my area. One is particle swarm optimization. And this was inspired by how flocks of birds or schools of fish would swim around, and they sort of cooperate and kind of communicate with each other. And somebody looked at that and said, hey, that could be an optimization algorithm looking for a local best, just like a school of fish would swim around. Older than that, and also hugely popular, are genetic algorithms, where you essentially describe your device with DNA, and you combine DNA and you have mutations and all this, just like how genetics work. And so these are searching globally. They very often find very good solutions, but there's no guarantee that it's the global best. If we're using randomness, it's probably because we don't know a lot about our solution space, and we don't know if we'll have the global best. So there's always the chance, if we get a design that's good enough, that there's something better out there. And that's actually kind of exciting. There's another one that's a bit of a special case called simulated annealing. Simulated annealing is where you have a pretty good guess of your solution. You just want to sort of randomly tweak some things because you think you can improve it. So in some ways, it's a lot like the gradient method, but maybe around your local best, it's not a nice smooth function. And so maybe you'd want to employ randomness to try to help improve that. So There's many, many more direct and stochastic optimization methods. This is just to give you an idea and what I see being applied most commonly in electromagnetics, although there's also always the latest and greatest that'll come out. Some notes on optimization. So the stochastic methods, the ones employing randomness, are best to use, I think, when you know very little about the global best solution or what that might look like. And so they also tend to search globally much better than the gradient methods. And at the end of the day, I am an engineer. I don't necessarily need to know that I have the absolute best solution or not. As long as my solution is good enough, I'm okay with that. So that's what we're just saying here. A lot of people, they'll argue, hey, this method is absolutely guaranteed to find the global best, and that's completely absurd, unless you know something about the solution space. But if you know something about the solution space, why are you employing an optimization algorithm? You can likely jump straight to it. But as engineers, we're satisfied with good enough type solutions. So given all that, the only way that you can ever guarantee that you have the global best solution, obviously, unless you know something, but assuming you don't know something special about the solution space, a complete search is the only way you're going to have that guarantee. Direct methods, they converge very fast, but only find local best solutions. So you can start to imagine maybe hybrids. Maybe you use stochastic optimizations when you think you might have a good solution. You use a direct method to zoom in on that local best. The other thing I'll mention, and I will hear many discussions about, genetic algorithms versus particle swarm versus topology optimization versus artificial intelligence, machine learning. In my experience with this, all these algorithms can be made to work, and I don't really see a real benefit one over the other unless there's like a special need or something special about the problem. What I do see, though, is that it all comes down to this merit function. We need something that in a single number tells us how good the function is. So in my research, I watch my students, they might work for a few months, they get their optimization working, but they spend the rest of their PhD working on that merit function. And even more, that merit function very often changes over the course of the optimization. At first, before any potential solutions are known, we have to relax the merit function and capture more stuff. As we start to have good solutions or learn more about what those good solutions are, we will tighten up our merit function and start to refine those. So even more, the merit function can change over the optimization. So in my opinion, the discussion should be much more about the merit function than the actual optimization algorithm. So let's talk about the merit function. The merit function, this is our single number function that tells us how good our solution is. And this is challenging when we have multiple things to consider. So back to our example, in this case, our merit function is the transmittance, or how much energy gets through in the zero order mode. We want it to be low. And so we'll write our merit function as a function of f and d. We actually know that it's a simulation determining that, but it returns the transmittance, and that's our merit function. So let's run with this. Let's rethink the merit function. We already mentioned some of this. Maybe the absolute global best is right here if we're considering only transmittance. However, look how narrow that is. We have to get F and D right on in order to get that. Well, what if our manufacturing can't do that? What if there's more slop in our manufacturing? Well, in which case, when we start considering that, maybe up here looks better. So very often in our optimizations, we not only consider the parameter that we're optimizing, but some kind of bandwidth or how much tolerance we have in that, because we want to design a device that's easy to make and won't fail if we don't make it exact. So there's a lot more to think about in the merit function. So we almost always have multiple considerations. Right now we have F, we have D, and now there's even a bandwidth consideration. How can we do this? And that I know of, there's not really a cookbook way of doing it, but here's one way to do that. We can calculate our merit function as a ratio. And let's say we want to make our merit function 0, 0 being the best solution. And we could turn that around where an infinity or something might be the best solution. But let's think about, we want to minimize the merit function to get to the best solution. All of the terms in the numerator, these are things that we would want to minimize in order to get to the best solution. Everything in the denominator are things we'd want to maximize to get to the best solution. So we can put it on the numerator or denominator, depending whether it's something we want to minimize or maximize. For example, maybe we want to minimize transmittance, but we want to maximize bandwidth. So we put 1 on the numerator, 1 on the denominator. Let's say our multiple considerations are not equally important. Let's say we have 3 things that we would like to maximize, A1, A2, and A3, but they're not equally important. So what if we multiplied them by a number A, B, and C, and maybe if A3 is the most important, I'd set C to 100, and if A2 and A1 are less important, maybe I set these to 10. So what happens if we do that? Well, we end up factoring A, B, and C out, and so no matter how I choose those, really our merit function is just A1 times A2 times A3. It's not that, this is doing nothing to help convey the relative importance of this. So that's not a good way to do it. How do we do it then? Well, there's a bunch of ways. We can use exponents to convey relative importance. We can take logarithms to sort of suppress the importance of this variable. We can also add constants. For example, suppose we're trying to minimize this. If there's a chance that A2 could go to 0, that would give us a perfect merit function, even if A1 and A3 are horrible. So if we just add 1 to that, that fixes that problem. Even when A2 is 0, then A1 and A3 can still affect the merit function. And then there's hybrids of all this. And I personally can't tell you which one is the best to use. I can just give you the tools and let you figure that out for yourself. One thing I can do for you is an example, and this is actually something from one of my past lives when I was working for Harris Corporation, and we had antennas that we wanted to optimize. And this is back in the 1990s when these types of genetic algorithms things were new. And I was looking for a merit function or cost function to optimize an antenna. So when it comes to antennas, very often you want them to be wideband. So bandwidth was a consideration. And we want them very efficient. It doesn't do any good to have a whole lot of bandwidth if it's a hugely inefficient antenna and that energy doesn't get transmitted anyway. So bandwidth times efficiency is a very common merit function to use. But I started thinking, is that the best? Are B, the bandwidth, and efficiency, are they actually equally important? Well, there's something called the Shannon capacity theorem that comes from communication theory. And it's basically giving you the capacity of your channel, how many bits per second can you squeeze through a channel, and here's the bandwidth of that channel, and here's the signal to noise ratio of the channel. Well, right away looking at that, that tells me that bandwidth and efficiency, which is related to the signal to noise, so bandwidth and efficiency aren't equally important. And depending what their values are, one or the other may become more important. So what I decided to do is basically use the Shannon capacity theorem. So I have to call this inspired by the Shannon capacity theorem because doing this optimization, I didn't have access to signal to noise ratio. So I put in efficiency in place of the signal to noise ratio. So this really is no longer the Shannon capacity theorem, but it sure is inspired by the Shannon capacity theorem. The other thing is, maybe we could get a really great antenna, but it's huge. It's way too big to even be usable by our customer at the time. So what I wanted to do then, in this case, we have a merit function that we want to maximize. So what I did is I divided by the size. So smaller antennas would actually increase the merit function. So now we have yet a new merit function. And so let's think about this. Are there any pitfalls with this merit function? There is. If we let this antenna size go to 0, or even something really, really small, even the smallest of antenna, it will have some bandwidth and it will have some efficiency. those don't go to zero. They'll be really poor. However, if we're dividing by a really small number, that can still make the merit function look huge. And that's probably not a design that we would like to get. And so this is not a sufficient merit function then, simply because putting L in the denominator like that can lead to false solutions. So what I chose to do was add 1 to L. So now this could even go to 0, but the denominator does not go to 0. And that still then listens some to the bandwidth and efficiency. Now, is that the world's best merit function? I don't know. But in the work I did, that was the merit function I went with, and that was the thinking behind it. And you can see that it takes a long time to get to the merit function. And as the optimizations improve, you might even want to change the merit function. And that has nothing even to do with the algorithm that we're using to optimize. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.